Namaste students. Now we are on the LPP problem. We are solving LPP problem graphically. In the last session we have seen two problems. One is of maximum and where we get only one solution, that is unique optimal solution. One more problem we have seen, that's also maximum problem where we get two answers as a solution, two maximum values. So if we get two value as answer, we consider it as, we conclude it as, that is multiple optimal solution. So we have seen the problem of unique optimal solution and multiple optimal solution. As I said, we have two more solutions, that is one is unbounded solution. What is that unbounded solution? And in other case there is no solution. So we see such kind of problems. Now here we are on the fourth problem in case of graphical type. That is, solve graphically the following. Maximum z is equal to 3x plus 2y subject to constraint x minus y, that is less than or equal to 1, and x plus y, that is greater than or equal to 3, and xy is greater than or equal to 0. So what is that first step? We have to consider unequal constraint as equal. Considering unequal constraint as equal. Now take the equations then. X minus y is equal to 1. This is first one. Then x plus y is equal to 3. This is second one. Now in the second step we need to find out two pairs of points for each equation. Now take the first equation there, that is x minus y is equal to 1. Here if x is equal to 0, what is the value of y? Y is equal to minus 1. Then if y is equal to 0, what is the value of x? X is equal to 1. Now see here, x and y, if x is equal to 0, value of y is minus 1, and if y is equal to 0, value of x is 1. Then take the second equation, that is x plus y is equal to 3. There if x is equal to 0, y is equal to 3, and if y is equal to 0, here x is equal to 3. Now if x is equal to 0, y is equal to 3. If y is equal to 0, x is equal to 3. Now we got two pairs of values for each equation. Now we need to represent on the graph. Now draw the x and y axis. Here x and, problem is with drawing graph only. I hope you are practicing it. You have to practice on the graph sheet, otherwise it will go wrong. This is x-axis, this is y-axis. Now see their x-axis. X-axis their maximum value is 3. So we can go like here it is 0, 1, 2, 3, 4. We can write 5 also. Write 5 if you have place over. Then y-axis you see. In the last section we have seen, in the last problem, one problem, there where we got value, the minus value in case of x series. Now we have minus value in case of y series. So where we have to extend? Here we have to extend. Now right here. So it is better to start from here minus 1. Minus 1. Then 1. What is the maximum value in case of y? There also 3. 1, 2, 3 and 4. Now write the scale. Scale you write x axis 1 centimeter. Let's say there also 1 unit. What are the units? 1. Now see the values. X is 0 there. X 1. Y also. Y is minus 1. So here 2. Here first equation we get the x minus 1 to y 1. So we have to extend it. Otherwise we will not find the feasible region of maximum or minimum value. Then next equation is it. X is 3 there. X is 3. Then what is y? Y is also 3. This is from second equation. 3 to 3. Now write the equations. What is the first equation? X minus y. So this is from the first equation. X minus y is equal to 1. This is from second equation. That is x plus y is equal to 3. So this is the second equation. This is the first equation. So we'll see there. Now see that first equation. See the first equation. X minus 1 less than. So this equation, it is less than, what did I say? Less than means it moves towards the origin. Origin is 0. Move towards the origin means we cannot draw like this. Because it is away from the origin. Origin means it should go this side. So this side. Okay. This is towards origin. In case of first equation, because it comes down here, y-axis, so it goes like this from the first equation. See here, origin is here, equation starts from here, moves towards the origin. So it goes like this. Now, from second equation is, you see, second equation is greater than. This is second equation, it goes away. It doesn't come here. This side means it coming towards the origin. So it is greater than, it should move away. It is moving away. Away means it goes like this. Now, which is the feasible region? Where lines of both the equations are falling. Which equation? Here the lines of falling. Till here, here is the line of only first equation. Here is also the line of only first equation. Here there is no line showing. Here the lines of which equation? Second equation. So this is the region where lines of both the equations will fall. So this region we consider it as feasible region. That is the feasible region for this particular problem. Other lines you have to erase. This is not necessary. Now this is our feasible region. Now we have got the feasible region for this particular problem. Now identify the corners. Identify the corner. When we identify, here we can get 1, here we can get 1. And see that here, see the feasible region. Is there boundaries for this feasible region? For example, in previous problem we used to get the boundaries. Either if we get feasible region here we have boundaries on, here also we have boundary, here, so we have the boundary. Here if we get feasible region, here it's also within the boundary. Here if we don't have boundary on this side, here also there is no boundary. So this kind of problem, or this kind of solution we call it as unbounded solution. This kind of solution we call as unbounded solution, where there is no proper boundaries for the feasible region. And in this case, you have to see when you get unbounded solution means unbounded feasible region, you have to see whether your problem is of maximum or minimum. Here, if your feasible region is unbounded and problem is of maximum type means you have to conclude your problem here itself. Because for an unbounded region or unbounded solution, maximum value you cannot find out. Maximum value goes on increasing, it's an infinity. Maximum value for unbounded solution is an infinity. So your problem ends here only. So you are not getting corner points also. You will get only 2 corner points, not more than that. So you are not preparing that particular table. Which one? Corner points and that values. You have to conclude here itself. The given LPP has unbounded solution. Since it is a maximum problem, you have to stop there. Now, for example, unbounded This is an unbounded problem and problem is of minimum type. If it is a minimum problem means minimum values you can get. You cannot get maximum value. Minimum you can get. Minimum means again you are continuing. You are preparing corner points and you are getting the minimum value. Because you will get here two boundaries, you will get, with that you are finding out the values. So, see here, listen carefully. If it is an unbounded maximum problem, your problem ends here itself. But if it's an unbounded minimum problem ends, you have to continue. So, this given problem is unbounded and also maximum. We cannot get maximum value. Maximum value, it goes on increasing. It is in an infinite number. So, we are not finding the maximum value. We are concluding here itself. The given LPP has unbounded solution. This is the conclusion. Here your problem ends. Now same problem if it comes for minimum, you are continuing and you have to conclude them. What is the minimum value? You will get their minimum value. Since it's the maximum value, this is the conclusion. Here it is the end of this particular problem. Remember, unbounded maximum, here it ends. We'll see other kind of problem. We'll see now other kind of problem. Now, this is of minimum type. Minimum z is equal to 20x plus 40y and 6x plus y is greater than or equal to 18. X plus 4y greater than or equal to 12 and y is greater than or equal to 0. 1 minute. Problem okay, correct. Signs both are greater than. Now we'll consider the unequal constraints as considering unequal constraint as equal. Then take the equation, that is 6x plus y is equal to 18. That is first equation. Now second one, x plus 4y is equal to 12. That is second equation. Now we have made unequal constraints as equals. Now take the first equation, that is 6x plus y is equal to 18. If x is equal to 0, y is equal to 18, then if y is equal to 0, what will remain? 6x is equal to 18 will remain. X is equal to 18 by 6. So what is the value of x? X we get as 3. So here we get values as x, y. First one 0 and 18. Here when y is 18, x is 3. Next one, we will take the second equation. That is x plus 4y is equal to 12. Now here, if x is equal to 0, what will remain? 4y is equal to 12. So y is equal to 12 by 4. So y is equal to 12. Now, if y is equal to 0, then x is equal to 12. So what values we have got here? We got values as, when x is 0, y is 3. Y is 3. Then when y is 0, x is 12. Now we got two pair of points for each equation. Now plot this on the graph. Now take x and y axis. X and y axis. x-axis, y-axis. Now see the values. Now values you see on the x-axis. Here it is 3. We have to extend till 12. So we'll take values as 2, 4, 6, 8, 10, then 12. Grade 1, 14. Next one, that is y-axis you see. Here it is 18, 3. Smaller one is 3. So we'll extend 3, then 6, 3, 6, 9, 12, then 15, 18. Then one more if you want to write, that is 21. So now we write the scale here. We write the scale. Now take the scale. X-axis is equal to 1 centimeter. What units we have taken? 2 units. The gap of 2 there. Y-axis is equal to 1 centimeter. What are the units we have taken? 3 units. 3, 6, 9, 12. Now see the equation there. From the first equation, what do we get? X is 0 and x is 0, y is 18. Then 18, then here x is around 3 means we'll make it here, that is 3. So here we get value as 8 into 3, 8 into 3. 8 into 3. Now second equation, x is 0, y is 3 and here x is 12, y is 3. So let's see to 12. So we get here like this. So 3 to 12. Now see the sign over there. Both the equation has greater than sign. Which is the first equation? This is the first equation. What is that? 6x plus y is equal to 18. The second equation, x plus 4y is equal to 12. Now, here both the equations are of more than 10. So, it moves away from the origin. So, both the equation, it moves away from the origin. This also, even this also moves away from the origin. So, which is the common region? This cannot be a common region. Here lines of only second equation will come. So, here there is no lines of any of the equation. Here the lines of first equation will come slightly. So, which is the common region? Where the lines of both the equation will fall. So, this is the common region. That is a feasible region for this particular problem. So, this is the feasible region. This is the feasible region for this particular problem. And see, this is also type of unbounded. This is there any boundaries over here? We have boundaries on this side, but here there is no boundaries. So this is unbounded problem here. But see the given problem here, it's of minimum time. What did I say when I was explaining previous problem? If it is a unbounded problem, if it's of minimum time, then we have to continue with the corner points. We can obtain minimum value. If it's a maximum problem, then we are stopping it here itself. But since it is a minimum problem, we are continuing. It's not a maximum problem. Maximum value we cannot get. Now, how many corner points we can obtain? We can obtain one corner points here, one more here B, and one more C here. Where two lines will intersect for this corner. For these corner points of feasible region. Now this is unbounded, no boundary here this side. Since we are Even though it is unbounded, we are continuing because it is a minimum problem. Now we will see what values we get to the corner points as a minimum value. Corner points, and what is the equation? 20x plus 40y, and which are the three corner points? That is A, B and C. Now we have to obtain values here. What are the values for A? A we get as x we get as 0. Y value we know, that is 18 and 18. Then we'll see for B. B what we may get there? We can get here around B value we get 1 is here. Then one more is here. Around here and here. Here we can take it as 2 point something. We'll take it here as 2.4 or 2.6 we'll take. We'll take 2.6. And this side also it goes something, we'll take 2.4. Here if you see you will get different, but I will go how we have got in the textbook. It is 2.4 and 2.6. Then for corner point C, that is, see here it is 0 and this one is 12. So 12, 0. X is 12 and other one is 0. Now substitute it. Here 20 into 0 plus 40 into 18. So this becomes 0. Here we get 720. Now this one, corner point B. That is 20 into 2.6 plus 40 into 2.4 is equal to, here we get as 148. Now here 20 into 12 plus 40 into 0, here we get as 240. Now see the problem. The problem is of minimum type. Problem is of minimum type. Which is the minimum value? 720, 240, 148. 148 is the minimum value. So we have to conclude the given LPP has what solution? Unique. Only one solution. Unique optimal solution, and the solution is Z is equal to 148, that is minimum, where X is equal to 2.4 we have taken, and 2.4 or 2.6 and 2.4. You may get different answer. If you plot it on the graph, here you will get the same value. This I have taken same textbook answer. Here it is slightly different. So we cannot take exact value there because we have not taken what's proper scale of measurement here. So this is about unbounded with minimum. Now in today's session we have seen unbounded problem with maximum, what we have to do, we are stopping it there. And unbounded problem with minimum, what we have to do. Minimum means we are continuing. Unbounded maximum means we cannot obtain, since we get there. For Z we get infinite value. So this is about unbounded solution. Now in the next session we will see when we may get no solution for the particular problem, how we need to conclude and what we need to do. So winding up with today's session.